Hey everybody, we are live and in studio. I started the recording today. Obviously, is the last class for Group 17. Hopefully, the last class for Group 17. Inshallah, the last class for Group 17. And we're just going to finish it off. In the last class, we learned what Group 17 was. They were called halogens, and they were called halogens because they were salt formers. Halo means salt, and gens means makers or formers. They were salt formers. We learned a lot about halogens, and it was largely a recap for halogens, and especially the recap of the displacement reaction that you studied from O levels and IGCSE, where a more reactive halogen displaces the less reactive halogen from its salt solution, right? And that was the displacement reaction. And we learned that, normally when displacement reaction takes place, for example, chlorine displaces the bromine in its salt solution of NaBr, or maybe bromine displaces iodine in its salt solution of NaI. What ends up happening is Br2 aqueous forms here, I2 aqueous forms here, and they're both yellowish orange. They're both yellowish brown or yellowish orange. I call it yellowish brown. Yellowish brown kehte hain, whatever. And this is also orange, or you could call it yellowish brown. Same thing. Yellowish brown is effectively orange. So yellowish brown, they're both yellowish brown. And the problem is it's difficult to distinguish between the two. This has never been tested, but it can be tested. How do you distinguish between the two? You use a non-polar solvent called cyclohexane, because in cyclohexane you'll realize that you have different colors. You get, for chlorine aqueous, you get the same pale yellow green color, and for if it's like Br2, if you add Br2 to it, it's gonna have the color of Br2 aqueous in cyclohexane, which is what? Yellowish brown or orange, yellowish brown or orange. And the beauty is that if you add iodine in cyclohexane, if you take this I2 aqueous and add it to cyclohexane, you're gonna get obviously a purple layer or a purple color. So how could you distinguish between whether it's Br2 aqueous or I2 aqueous? You use cyclohexane, which is a non-polar organic solvent. So it's called a non-polar solvent or an organic solvent. Organic solvent, aka non-polar, right? So they give you different colors, right? For chlorine, it gives you the color of chlorine, which is pale yellow green gas. Br2 ke liye, it gives you the yellowish brown color, or you could even call it orange. And I2 is purple, it gives you a purple color, the same color that iodine has in I2 gas. It gives you the same color that iodine has in I2 gas. That's it. And you see that beautiful layers forming, because obviously they are not miscible liquid. Cyclohexane is not miscible with water. So there are layers forming, right? There are layers forming. And that's the idea. And then we also studied the idea of reactivity. So if you go from fluorine to chlorine to bromine to iodine, we realize that down the group, what happens to the oxidizing power, the ability of an atom to attract electrons, the power of an atom to attract electrons to itself, the oxidizing power decreases, right? And what happens to the volatility? The volatility is the ability to escape, for liquid particles to escape into the air, right? For particles to escape into the air. This is already a gas. This is already a gas. This is a liquid. This is a solid. And because liquids have weaker van der Waals compared to solids, so relatively, we know that volatility down the group, volatility also decreases because it's difficult to escape into the air. And the reason for that is pretty simple. All the reasons right here, the reasons for oxidizing power decreasing has to do with electronegativity, and the reason for volatility decreasing or melting point and boiling point increasing is what? These two ideas are related to the van der Waals. The van der Waals due to ID interactions, they increase. Why? Because you have more number of electrons. This is all recap. We've already done everything. Then we also talked about reactivity for non-metals. They largely depend on how quickly they can gain electrons, aka how electronegative they are. So because the electronegativity decreases, the reactivity also decreases down the group, right? And if you talk about halide ions, which are the negative ions of group 7, which is fluoride, chloride, bromide, and iodide, these negative ions they are good reducing agents. They have reducing powers, right? They're good reducing agents. And down the group, you realize that the reducing power actually increases. Reducing power increases. Why does the reducing power increases? Because see, reducing power has to do with what? How easily it can reduce another substance, aka how easily it can give electron. And down the group, the size becomes larger. Iodide ion is much larger than the fluoride ion, so it's easy for this to give electrons. That's why the reducing power increases, right? That's the idea. And we've already studied all of this good stuff in the last class. And then we learned how they can react with halogens, how halogens can react with hydrogen to give you a hydrogen halide. And the idea was pretty simple. The idea had to do with halogens, because they are oxidizing agents, obviously, and they have oxidizing power. The greater the oxidizing power, the quicker the reaction, the faster the reaction, and aka that's the reason why fluorine was reacting explosively with hydrogen. Even in a dark room under cool conditions, you were getting HF, right? And the reason why chlorine was reacting with hydrogen, but you needed, sunlight for that. You needed sunlight. That's when it was reacting explosively. And then for bromine to react with hydrogen, it was a slow reaction even in sunlight. So it was slow even on heating, in sunlight, aka also heating, And then iodine, I2, when it reacts with hydrogen, it literally forms an equilibrium, Hi, but equilibrium. This is HBr and that's HCl. So this is literally, it forms an equilibrium. So slow, it's so slow, forms an equilibrium. You need to provide it with heat. Heating is important. So that's the idea. Now, today what we need to learn is, this is all a recap of the last class, major chunks. Today we need to look at our hydrogen halides, because now we know how to make hydrogen halides. How do you make hydrogen halides? Well, we know it. You literally take a halogen and react it with hydrogen. And because they are oxidizing agents, they're going to take in electrons from hydrogen and become the halide ion, the fluoride ion, the chloride ion, the bromide ion, the iodide ion, right? Or you could call it, we call them ions once they obviously are in aqueous solutions. In this case, they are just hydrogen fluoride, this is hydrogen chloride, hydrogen bromide, hydrogen iodide, right? So they are simple molecular structures right here, simple molecular structures. But if you dissolve them in water, they form ions, right? That's the acid. Hydrogen ion, fluoride ion, chloride ion, hydrogen ion, bromide ion, hydrogen ion, iodide ion. But in this case, it's hydrogen fluoride. In aqueous case, it would be known as hydrofluoric acid, because it becomes acid. Here, it's known as hydrogen chloride. In aqueous, it's known as hydrochloric acid. Here, hydrogen bromide. In aqueous, it's going to be known as hydrobromic acid. Hydroiodic acid. In aqueous, here, it's hydrogen iodide. Now, once we know how to form these compounds, or these beautiful molecules of HF, HCl, HBr, HI, you know how to form this. How do you form this? Take hydrogen and react it with halogens. And this reaction is going to be pretty fast. Making hydrogen fluoride is going to be the quickest. And we know the reason, because fluorine is the strongest, has the strongest oxidizing power. It is the smallest out of all of them. It's going to attract the electrons, and bond very quickly. The distance from the outermost electron and the nucleus for fluorine is pretty small. And all of that idea, So this is going to be very quick and blah, blah, blah. We already studied that. Now, the idea is, if I show their bonding, it's obviously H bonded to F. I'm not talking about the aqueous state. I'm talking about the covalent bond. So H bonded to Br, H bonded to I. If I just talk about the bonding, my question to you guys is, which of these bonds is going to be the strongest? Which of these bonds is going to be the strongest? Strength of this sigma bond. These are all sigma bonds. And we've already discussed this in chapter number 2. Here I'm just consolidating it. You should know which of these is strongest. Think about the idea between sigma bonds. Why would a particular sigma bond be stronger than another sigma bond? Why? The orbital overlap. Remember, the orbital overlap. You realize that fluorine is much smaller than chlorine, which is much smaller than bromine, which is much smaller than iodine. And you realize that down the group, what's happening is the halogen atom becomes larger. So you have a larger halogen atom down the group. We've already studied this in chemical bonding, to be honest, frankly speaking. So you have a larger halogen atom down the group. If there's a larger halogen atom down the group, let's suppose these are my nuclei, right? If you have a larger halogen atom down the group, what happens? The distance between the nuclei increases. So the distance the internuclear distance. If you want to be more scientific like me, you could say, hey, the internuclear distance increases. Or the distance between two nuclei increase, right? Because if it's larger, the nucleuses are further apart for hydrogen and fluorine. So the internuclear distances actually increase down the group, right? Because it's a larger atom. The distance between the two nuclei is larger, which results in what? Which results in weaker attraction or stronger attraction? Which results in what? It results in weaker net attraction on the shared pair of electrons, for the shared pair of electrons. Right? That's what a covalent bond is, the shared pair of electrons. So there's weaker attraction, weaker net attraction, or weaker nuclear attraction for the shared pair of electrons. And so obviously the bond strength decreases. The strength of the bond decreases. And you could even say, hey, the bond length increases or decreases down the group. The length of the bond. The length of the bond, obviously, what happens to the length of the bond? What happens to the length of the bond? Because it's a larger atom, the length of the bond obviously increases down the group, right? Because the distance between the two nuclei is larger. So bond length also increases. Strength decreases due to bond length increasing. And why does the bond length increase? That's the reason. If somebody were to ask you in 2 words, in 2 phrases, can you tell me why the bond strength decreases? Well, you say the bond strength decreases down group 17 because the bond length increases. Okay, why does the bond length increase then? Well, the bond length increases because you have a larger halogen atom, the internuclear distance increases between the 2 atoms, and this results in weaker nuclear attraction for the shared pair of electrons, and therefore the length of the bond obviously increases. Larger atom, right? And you could also say that, hey, because it's a larger atom, there's less orbital overlap. And we've studied this in chapter number 2. The larger the atom you have, the less the orbital overlap. That's also what results in a weaker bond down the group. And you could prove it literally by looking at their bond energies. So bond energy is basically the energy, bond energies are basically the energies which are required to break or make these bonds, right? For now, just understand it's the energy required to break these bonds. So my question to you guys is, if I break HF bond, it requires a lot of energy, 562 kilojoules per mole. You have to provide this much energy to break every 1 mole of HF bond. Have to provide this, and you see the bond energies are decreasing. So you tell the examiner, hey, I know that down the group the strength of the bond decreases. I know that down the group the strength of the bond decreases. There are effectively 2 reasons to it. Number uno, the bond length increases, and number dos, the bond energies decrease. The bond energies down the group decreases. You require less energy to break the bond. So that's why we say the strength of bond decreases, because the bond length increases, number 1. And number 2, the bond energies decrease. You require less energy to break a particular bond, to break the HCl bond compared to the HF bond. And what's the reason? The reason is again the same. There's less orbital overlap, larger halogen atom, internuclear distances increases, Sir, I don't understand larger orbital overlap. Kiddo, I've already taught this in chapter number 2. But hey, let me see if I could still find the diagram. Let me see if I can find the diagram for it. I've taught this in chapter 2, to be honest. Why am I saying to be honest? I'm looking for the diagram just to show you. It's just for you. See, I don't have the exact diagram for HF or what, but you see, the larger the atom that you have, see, silicon atom is much larger than O atom. C and O are smaller atoms compared to the silicon atom and the oxygen. See, if the silicon atom is larger, the orbital overlap is this fella right here. See, in this case, the orbital overlap is larger in CO's case, but in SiO case, the orbital overlap is smaller. We know. See, the p orbitals of different size produce little overlap. But this is in terms of pi bonds. This is in terms of pi bonds. This literally applies to any other bond. If it's a lengthier bond, the length of the bond is longer, that means the orbital overlap is less, right? Okay, this is all sigma bonds, no pi bond. Please, I just had to prove it to you that larger atom means smaller, less orbital overlap. Done. So that's the idea behind it. Now, if I were to ask you guys if HF, HCl, HBr, HI, which of these have the strongest bonds? Which of these have the strongest bonds? And before I ask you this, my question to you guys is that, chalo, this is the question. Which of these have the strongest bonds? Does HF have the strongest bond? Does HCl have the strongest bond? HBr has the strongest bond? Or HI has the strongest bond? Which of these has the strongest bond? Obviously HF, because it's smaller in size. You could even make it for yourself like this. I used to do it like this, and I used to say, hey, hold up. HF has the strongest bond, strongest sigma bond, strongest bond. And what's the reason? Two reasons. Number one, it has a shorter bond length, and number two, it has a higher bond energy. And what's the reason? What's the reason for these two? Well, because fluorine atom is smaller. This is the further reasoning. Fluorine atom is smaller. It's smaller. Distance between the internuclear distance is reduced between fluorine and hydrogen. Distance is reduced between fluorine and H. Stronger nuclear attraction. Stronger nuclear attraction for the shared pair of electrons. Yes, that's the idea. Now, the next concept from this, we transition into the idea of reactivity. Now, in order for HF or HCl or HI or HBr to react, this bond must be broken first. Remember your O levels and IGCSE basics. If HF were to react with something and form something else, you need to first break this bond, right? You need to first break this bond. You need to first break this bond. You need to first break this bond. For HF to react, for HCl to react, for HBr to react, for HI to react, you need to first break their bonds. And once their bonds are broken, only then are they available to react with other species and form products, right? Like in O levels, I used to teach you old bonds must be broken for new bonds to form. Remember that? That, right? So my question to you guys is, if I talk about reactivity, which of these would be the most reactive? Would HF be the most reactive or HI be the most reactive? Would A be the most reactive or B would be the most reactive? Please do not confuse it with fluorine and iodine. That is a story. That's a whole different story. Fluorine and iodine, its reactivity had to do with electronegativity. And it's very important to clarify this concept. Very important. Fluorine is more electronegative than iodine, and therefore it's more reactive than iodine because the power to attract electrons to itself is pretty strong. The oxidizing power is pretty high compared to iodine's oxidizing power, right? So we know that reactivity decreases down the group for halogens. But what about halogen halides? Halogen halides कह रहा हूँ, hydrogen halides. What about hydrogen halides? What about them? Please do not confuse. This is the most common. The examiner says students cannot distinguish between the two. That's what the examiner has told us through his reports. Please understand these are two different things. One is a hydrogen halide, and for hydrogen halides reactivity, you have to look at how easily you can break this bond. And so my question to you guys is, after all of this knowledge, all of this concept, can you break the HF bond more easily or can you break the HI bond more easily? That's the reactivity for it. Please tell me, can you break the HF bond easily or the HI bond easily? Come on. Please, come on. Give me the idea. Hanji, bole. I can break the HI bond more easily because it's a larger atom, there's less orbital overlap, it's a longer bond, all of this, it has a lower bond energy, and so on and so forth. You can write all these points in the exam, all these points. And my suggestion to you would be to write these points in the exam to be safe. Always tell the examiner, I know everything. Don't contradict yourself. Don't write contradictory information which is irrelevant, but these are all relevant information, right? So for reactivity for hydrogen halides, the hydrogen halides reactivity is going to increase or decrease down the group, because all of you are saying that it's far easy to break the HI bond. Therefore, this means that it's very easy to make this reactive. It's very easy for this to react. So this is the most reactive out of all of them. So reactivity for hydrogen halides down the group increases. Reactivity for hydrogen halides down the group increases. Kasam se, I swear to you, I've never learnt anything, learnt anything. I've always used these concepts. मुझे आज तक I have not rote learned them. So you don't need to rote learn them. It's so basic, so simple. Look at them, visualize them. See, I used to do this in my exam. Back in the day, I remember, I should say, hey, this is the most reactive, because for this to react, I just need to break this bond. And it's easier to break this bond because of all of these reasons that we've studied. And it's pretty difficult to break this bond right here because of all of these reasons that I've studied. So the reactivity for hydrogen halides increases down the group, right? And that means if reactivity increases, that means I can break the bond easily. I can break this bond. I can provide it with energy and I can break the bond more easily. Break bonds easily. I can break the bonds easily because of two reasons. Number one, lower bond energies down the group. And number two, lower bond energies down the group. And number two, the length of the bond. Longer bonds down the group. And the reason we know. Bond energies decreases down the group, bond lengths increases, the length of the bond increases, obviously. You have longer bonds down the group. So it's easier to break these bonds. And the examiner can ask you this, why is it easy to break these bonds? Because it has lower bond energies, less energy is required to break them, and they are longer bonds. And if the examiner asks you why, you know why. Larger atom, less orbital overlap, there's weaker nuclear attraction for the shared pair of electrons, and you could break the covalent bond more easily, right? Good stuff. We know that. Now, breaking of this bond is related to a concept called thermal stability. So if you can break the bond easily, that means it's with the help of energy, right? In this case, we're talking about heat energy. Thermal stability means, like, you provide it with heat, and if it's thermally stable, it's not gonna break. The more stable it is, the less the chances of it breaking is, right? So if I look at the bonds being broken easily down the group, what does that tell me about thermal stability? Like, I am providing it with heat and it breaks. I provide it with heat, breaks, crack. I provide it with heat, pretty darn, requires a lot of heat to break, a lot of heat. And this one, even the most heat. So what would happen to the thermal stability down the group? Well, you know that down the group, I can break these bonds pretty easily with the help of heat. Tuck. Heat energy, tuck. Bonds break down the group because of two reasons. Bond energy decreases, the length of the bond increases, blah, blah, blah. So what happens to the thermal stability? How easily can you break the bond? Very easily. Down the group, you can break the bond very easily. So it is less thermally stable. Less thermally stable means it can't withstand, face the heat. You break it, tuck, which means if you provide it with heat, it's going to break. Like, for example, I provide all of them with the same amount of heat. Which of these would you expect to break? If I say, hey, out of all four, one is going to break, one bond is going to break. Which of these is expected to break if you provide it with heat? Out of these four, one is going to break. The HI bond is going to break. Why? Because it is less stable. The thermal stability is less. So what happens to the thermal stability down the group? Down the group, the thermal stability decreases. Thermal stability. Maza aa raha hai? No rote learning whatsoever. Zero rote learning. Zero. And that is the reason. And what's the reason for it? These two reasons. Tuck and tuck. And what's the reasons for these two? Right here. See, everything is connected. You guys can even visualize it now. Maza aa raha hai? Inorganic mein, there's no rote learning whatsoever. No rote learning. If you remember these concepts, things are going to be pretty easy. Pretty easy. Gupshup, halwa. Asan? And that is the reason, when scientists started to perform the experiments, scientists started to try to break them with the help of heat. They started to thermally decompose these hydrogen halides. Do you know what they found out? And this is extra stuff, may be tested somewhere, I don't know, but it is a part of your course. When they started to thermally break them, what do you think would have happened? What do you think would have happened? If they started to thermally break this, thermally decompose the hydrogen halide, started to thermally decompose the hydrogen halide, what do you think would have happened? What do you think would have happened? Obviously, when you thermally decompose it, you go back into what? H2 and I2. right? You go back into hydrogen and halogen, right? So that's what thermal decomposition is. You go back into their elemental forms, hydrogen and iodine. Do you know how easy it was to break them? They literally, what scientists did was they inserted a red hot wire. A red hot wire. This is HI gas, right? So they inserted a red hot wire. What would have happened when they inserted the red hot wire inside, into a sample of hydrogen iodide gas? What do you think would have happened? Purple fumes. Literally, iodine gas is purple, right? So purple fumes formed. Purple fumes were automatically seen. Why? Because you know that it is thermally less stable. The thermal stability is pretty low for HI. In fact, it's the least thermally stable out of all of them. Because again, reason is two reasons. Lengthier, the longer the bond length, the weaker, the longer the bond length, and the other reason is the lower bond energy. And these two are the reasons why it's less thermally stable. The thermal stability is lower. It has the least thermal stability. That's why the moment you inserted a red hot wire into a sample of hydrogen iodide gas, you see purple fumes of iodine vapor. That's the observation. It can be tested in an MCQ. Please, it can be tested. Whatever I'm teaching, everything can be tested. Please. Acha, what do you think would have happened to HF and HCl? HF is at the top. HCl is right beneath it. HF and HCl, they are not decomposed even when you provide temperatures of about 1500 degrees Celsius. That's how thermally stable they are. Even if I provide a temperature of 1500 degrees Celsius, up to this high temperatures, it still does not decompose. What's the reason? It's thermally more stable than HI. Thermally, absolutely, it's thermally more stable than HI. And the reason we know, two reasons. Bond energies, shorter bond lengths. Shorter bond energies. And why shorter bond? Well, the smaller the atom, the lower the distance, the internuclear distance, the stronger the nuclear attraction for the shared pair of electrons, and the stronger the bond. The shorter the bond, the closer they are. All of these things, right? Make sense? What about HBr? Well, HBr is more thermally stable than HI, obviously. And because obviously it has a higher bond energy and it has a shorter bond length compared to HI, but it's weaker compared to HF and HCl, right? So what about this? Well, it's not as stable as HCl, thermally stable as HCl and HF, but what happens is if you provide about 430 degrees Celsius of temperature, around 430, just relatively speaking, around 430 degrees Celsius of temperature, about 10% of HBr were thermally decomposed, about 10%. And to just give you guys an idea, if you provide the same temperature, the same 430 degrees Celsius temperature to HI, about 20% of HI would decompose. So it's almost like you could arguably you could say, relatively speaking, it's about like twice as strong as the HI bond. About twice as strong. But it's not exactly twice as strong because you see this right here. About relative terms. See, HBr bond breaks at 366. This breaks at about 300. So not twice, but stronger. But for the same temperature, it's about 20% of HI would decompose compared to HBr. So that's the idea. And I hope it made sense to you guys. Now, what happens is, sometimes what we do is, we take these hydrogen halides now. HF, HCl. Do you like the story? I'm trying to make it as storetical as possible. I don't even think if that's a word, but as theoretical. There's no word as theoretical, but I'm trying to develop a story right here. Trying to develop a story. Now what happens is, you now know this fella is the least reactive or the most reactive. Come on, least or most? Come on, Hanji. Thak. Least reactive, most reactive. Hanji, shabash. Least reactive. And you know the reason. You know the reason. Two reasons. Shorter bond length and shorter bond length and higher bond energies. The highest bond energy. And you know the reason for that. Smaller atom, blah, blah, whatever. If it's the least reactive, can I call it thermally stable? Is it the most thermally stable? It is. Most thermally stable. most thermally stable. Why? Same two reasons. Yeah, most thermally stable, same two reasons. Why have I drawn this line right here? Pretty simple. And then this one is the most reactive, same two reason, and least stable, the lowest thermal stability. Yeah. Now what happens is, and these are all simple molecular structures. Isn't that true? Hydrogen fluoride, simple molecular structures. Hydrogen fluoride, hydrogen chloride, hydrogen iodide, hydrogen bromide, all simple molecular. But the moment you add them to water, what happens? You've studied this in O levels and IGCSE. I'm going to go into the detail for it in chapter number 9. In chapter number 9, which is acid, bases, and salts. But the moment you add them to water, what do you get? You get HF aqueous. You get HCl aqueous. You get HBr aqueous. So the bonding changes. You go from a covalent bonding to what? To ions. You literally go from covalent bonding to free moving ions. Now you have ions. And HI goes into HI aqueous. Which means what? What does this mean? This means that an acid has formed. You get the H plus ions and the fluoride minus ions. And you've studied the definition for an acid, which is a proton donor. Any substance which gives you a proton, when dissolved in water, in this particular case, is an acid. So they are all acids. And that's why now you're not going to call it hydrogen fluoride. The naming changed. Now it's called hydrofluoric acid. Hydrochloric acid. Hydrobromic acid. Hydroiodic acid. Yes? They're all aqueous now. Aqueous, 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 and AQ. Makes sense. They're all acids. All acids. All acids. All of these things can be tested in the exams, by the way, and especially in MCQs. So it's very important to be very attentive here. Very attentive here. My question to you guys is, although, I'll give you guys a little detail about an acid, because you must have already studied this in O levels and IGCs, but an acid is a proton donor, right? A hydrogen ion is effectively a proton, right? Because hydrogen is 1,1. So if it's a hydrogen ion, it just is a single proton. It has no neutron, and because it's 1 plus, it has no electron. So an acid is effectively a hydrogen ion donor or a proton donor, right? A proton donor. And you'll study more about this in chapter number 9, but from O levels, it's a proton donor. And the moment you take these hydrogens covalently bonded to chlorine, bromine, fluorine, iodine, and you add it to water, it literally dissociates to give you guys protons. The bonding literally changes. You go from a covalent bonding to free moving ions, right? That's why acids can even conduct electricity, because they have mobile ions, not electrons, mobile ions, free moving ions, which can carry charge, obviously, right? Now, it's so beautiful to just appreciate chemistry right here. Because we know that which acid is pretty strong. We should know this from O levels and IGCSE, and you'll learn this even in chapter number 9, but which acid is strong? A strong acid is the one that gives you more, for now just understand, that gives you more and more H plus ions. The more H plus ions it gives you, the higher the strength. That's why we say a strong acid is an acid which fully dissociates when dissolved in water, which fully ionizes, gives you so many hydrogen ions. And the one that will give you hydrogen ions, less hydrogen ions, it'll still be an acid, but it'll be a relatively weaker acid. Now use the idea of hydrogen ions, and tell me which acid is going to be the strongest acid. Hydrofluoric acid, hydrochloric acid, hydrobromic acid, or please, tukke nahi marne. No sati, no tukke. No ternalia. Give me proper reasoning for it. Think about it. See, the more hydrogen ions we're going to have, the stronger the acid, right? Now the question is, how would you get more hydrogen ions? Well, more of the HF would go into aqueous, right? The HF bond would break and you would get more aqueous. Now, my question to you guys is, which bond is easier to break? This. Shabash. Use your brain. Absolutely, Yahya is on to something. Yahya has given me the correct option. Yeah, Yahya has given me the correct option. The reasoning can be absolutely. Aisha has given me the correct option, and I love Aisha's reasoning. Aisha is saying, sir, between all of these, we know that this is a pretty strong bond. So for this to dissociate into ions and give you an acid, it's a little difficult because the strength of the bond is pretty strong, right? It has higher bond energy, the highest bond energy, and the length of the bond is shorter, and we know the reasons for that, and therefore it's the least reactive even, and it won't dissociate that much compared to this, and compared to this. So out of all of them, the HI would dissociate the most because of the weakest bond. Why does it have a weakest bond? Because number one, it has the longest bond length, and it has the lowest bond energy. So it's the weakest bond. It very easily dissociates, and that is the reason why HI aqueous is effectively the strongest acid out of all of them. So all of these things are tested in MCQs. Now it makes sense. Maza aa raha hai? No rote learning whatsoever. Nothing of that sort. So that's the second story. So we started our story right here from hydrogen halides, and we said, how are these hydrogen halides formed? We learned that in yesterday's class. See, please, I want to consolidate everything. How are hydrogen halides formed? Like this. And the reactivity decreases down the halogen group, right? So all of these ideas should be in your brain. You know that if you want to form HF, it's the fastest, the quickest reaction. HF quickest. And we learned how HF, HBr, HCl, HI was formed. Once they were formed, we started to study their bond strengths. And we said, hey, this is pretty strong. And that's why it is going to be the least reactive. So just like fluorine was the most reactive, the hydrogen fluoride is the least reactive, right? And then it's also hydrofluoric acid is also the weakest acid. So fluorine was very reactive, but hydrogen fluoride was, a pretty strong bond, and therefore it was the least reactive. It was thermally the most stable and whatnot. And then hydrofluoric acid was also the weakest acid because it did not dissociate as much as hydroiodic acid, and the reason for that was the strength of the bond, which depended on bond energies and the length of the bond. Maza aaya? So all these three things are different. The acid, the hydrogen fluoride, makki, mardi, bach gaya, manhoos, bach gayi makki. Machar or makki, what's that called? Mosquito. So that's the idea. Maza aaya? Now, moving forward. Please, I need to finish this today. I've just taught a 37-minute class. You guys can take a break, 2 minutes break, and then we will move forward. Once I'm connecting everything. See, it's like a story. Once these ions are formed, these are ions effectively, right? These acids are free-moving ions. They're free-moving ions. Now, these ions have certain reactions. See, you have the fluoride ion, the chloride ion, the bromide ion, the iodide ion. And these ions have certain reactions. Reactions of these halides. And it's also like the identification of halides. Because the problem was that even though you know which acid is strong and which acid is weaker, the problem is they're all colorless. So for example, Sir Suleiman wanted you guys, there are 4 bottles, and I'm saying they're all group 7 acids, right? One is hydrofluoric acid, one is hydrochloric acid, one is hydroiodic acid, one is hydrobromic acid, and I need the strongest acid, which is what? Hydroiodic acid, right? The strongest acid is hydroiodic acid. I need strongest acid, but the problem is they're all colorless. How do you figure out which one is hydroiodic acid, which one is hydrobromic acid, which one is hydrofluoric acid, which one is hydrochloric acid? By testing for these negative ions. These negative ions are going to tell you. Obviously, you guys can argue with me if you've studied O-level chemistry. You guys just just use a pH meter. Okay, relax. We're not going to do that. I know you can, but whatever. We're not going to do this. So just use a pH. No. I want to test for these ions, because once I know which ion I have, I know which acid I'm talking about, right? So they're all colorless, and now I'm going to test for these ions, these negative ions. And again, you've studied this in O levels and IGCSE, but hey, you just study one extra detail here. So I'm going to test for the fluorides, the chlorides, the bromides, and the iodides. And once I figure out which ion I have, which halide ion I have, I know which acid I'm talking about. Yeah. Achha, one more thing, guys. Before I move forward, I hope you know how to write ionic equations. I hope you know how to write ionic equation. Please, this is also part of your course. Like chlorine reacts with NaBr right here. Sorry, I'm going a little back in time. But if chlorine reacts with NaBr, this displaces this fella right here. You get NaCl plus Br2 aqueous. I hope you know how to write ionic equations. You just split everything into ions. This is aqueous already. And this is a simple, it's a covalent molecule, right? So you can't split it into ions. NaBr is an ionic compound, so you can split it into the sodium ion and the bromide ion. The sodium ion and the bromide ion chloride ion can also be split here. They're all aqueous, aqueous, and aqueous, and aqueous, right? And Br2 is covalent molecule, so it can't be split into ions. This sodium ion is the spectator ion, which do not take part in the reaction. And this is the ionic equation. So 2Br minus, I'm just balancing it, 2 chloride ions plus Br2. This is the ionic equation for this, right? Because remember, these chloride ions and bromide ions must be bonded to a positive ions. The moment you understand this, 50% of your chemistry starts to make sense. These negative ions are bonded to a positive ions, but the reason we don't write the positive ions is because they don't take part in the reaction. We don't care about them. They're useless for us because they don't take part in the reaction. Similarly, if I were to test for the chloride ion, the bromide ion, the iodide ion, the fluoride ion, these ions must be bonded to some positive ions. How are these ions formed? Asman mein to nahi tapke na? They must be bonded to a particular positive ion. There must be accompanied by a positive ion. But the reason I'm not writing those positive ions is because I couldn't care less. Couldn't care less indeed, right? So how do we test for these ions? In our course, it's just chloride ion, bromide ion, and iodide ion. Fluoride, not a part of our course because fluoride is a little tricky. Fluorine in general is also very tricky, and so is its ion. But hey, how do we know that there's chloride ion, bromide ion, and iodide ion? That's the next step, right? So reaction of halides. And we're almost done with this chapter, almost. Then we're just left with nitrogen and sulfur. Any questions up until now? Guys, when will we touch 100 students? We're so close. Can we touch the 100 students by the end of December? That'll be awesome. When your peers will fail in their December exams, they'll ask you, sir, kis sir se pad rahe hain? What is going on? And you're gonna gatekeep me. Please don't gatekeep me. I want to become famous. I want that one day in my class there are 100 students sitting in the live class. Although we are so close to 100, but they're not sitting in the live class, are they? I'm struggling in every subject except for chemistry. I'm glad, Safa, that you are not struggling with chemistry. लेकिन I hope मज़ा आ रहा है आपको, हैं? आपकी टीचर तो आपको तंग नहीं कर रही. Was it you, Safa, whose teacher was probably your nemesis, and coming at you for studying from me? I think she should also study from me. No, I'm joking. मज़ाक कर रहा हूँ. खैर. Now, the idea is to test for these halide ions. I need to give you guys a little recap of O level and IGCSE. In O levels, remember, you learned solubility rules. And in solubility rules, you learned that all group 7 ions are soluble except for LMS. What is LMS? Lead, mercury, silver. This was a general solubility rule that I taught you guys, remember? All group 7 ions are soluble in water except for lead chloride, lead bromide, lead iodide, mercury chloride, bromide iodide, silver chloride, bromide iodide. All group 7s are soluble except for these. And in our course, you just need to know silver, right? So if I have silver chloride, would it be soluble in water? No. Would it dissolve in water? No. If I have silver bromide, would it dissolve in water? No. If I have silver iodide, would it dissolve in water? No. It doesn't. It's insoluble. It doesn't dissolve, right? That's the idea. It doesn't dissolve. All group 7s are soluble except for group 7 salts, except for silver, lead, mercury, silver, LMS. But in our course, we just have silver. We just need to know about silver, right? Now, the idea is, if in a particular container, if in a particular test tube, I have the chloride ion, and in this particular test tube I have the bromide ion, and in this particular test tube I have like the iodide ion, and I add silver ions to it. Obviously initially, they're colorless. If I add silver ions to it, a solid is going to form called AgCl, silver chloride. Another solid is going to precipitate. We say a precipitate forms. Precipitate is a solid that forms. Silver bromide solid forms. Silver iodide solid forms, right? It's basically the silver ion comes into contact with the chloride ion and forms AgCl, right? Solid. These are both aqueous. Silver ion aqueous, chloride ion aqueous. Similarly, the same thing happens here. The silver ion comes into contact with the bromide ion, forms silver bromide, right? Solid. A precipitate forms. Similarly, the silver ion comes into contact with the iodide ion aqueous. Aqueous give you silver iodide, right? Which is obviously a precipitate. It's obviously a precipitate. Now again, I want to open your brains a little right here. My question to you guys is the chloride ion going to exist alone, or is there going to be some sort of positive ion with it? Why am I not writing that positive ion? Why am I not writing that positive ion? My question. Why am I not writing that positive ion? Because it's a spectator ion. I don't care. I couldn't care less. Would the silver ion exist alone? Is there, when I say you have add the silver ion, where do you get this silver ion from? Obviously it must be, it must be in contact with some negative ion. It must be in contact with some negative ion. Why have I not written that negative ion? Why have I not written that negative ion? This is the ionic equation for it, by the way. Why have I not written the negative ion for it? Why? Because I couldn't care less. It's a spectator ion. And what negative ion is there with the silver ion? Well, you need to make sure that whatever silver solution you add, it's soluble, right? So how would you get a silver ion? If it's bonded to a particular negative ion, which gives you a soluble solution of silver, right? And what is that? That negative ion is the nitrate ion. So basically what we are adding is not just the silver ion, we are adding silver nitrate. We're adding the silver nitrate solution. But why have I not written the nitrate ion here? Because I couldn't care less. It's spectator ion. Similarly here, the chloride ion in this solution, in this particular case, it was the hydrogen chloride, right? Which is basically hydrochloric acid. It was the hydrogen ion being bonded to the chloride ion, the hydrogen ion and the bromide ion, the hydrogen ion and the iodide ion. But it could also be the sodium ion and the iodide ion, the sodium ion and the bromide, the potassium ion and the bromide ion, because they're all soluble solutions, right? So if I have chloride, bromide, iodide, they must be with a positive ion which is soluble. That's why I'm not writing that positive ion, spectator ion, right? So this particular equation is the ionic equation for it. That's the ionic equation. We am ignoring all the positive ions. But if I did not ignore these positive ions, normally speaking, you could have silver nitrate, this is the full equation for it. You take silver nitrate, full equation, right? And let's suppose the chloride ion that I have is soluble. Obviously, it's dissolved in water. It's soluble in water. And I'll take sodium chloride because I know sodium chloride is soluble. Potassium, all group 1 chlorides and group 1 salts are all soluble in water. So sodium chloride, I could have taken sodium chloride. What would form? I know that out of this silver nitrate and sodium chloride, this silver ion would have come into contact with the chloride aqueous ion, and you would get AgCl solid. And what would be left behind in the solution? In the solution, you would have been left behind with the sodium ion and the nitrate ion. So you would be left behind with NaNO3 aqueous. Make sense? The same idea. I'll use the same thing, but in this case, I'll use like maybe potassium bromide because that's also aqueous. If I add them, I'm going to get AgBr. The silver ion is going to displace, the silver ion not displace, it's a precipitation reaction. So silver ion is going to come into contact with the bromide ion and you're going to form AgBr. It's effectively, this is what's happening. So you have the silver ion, the bromide ion, the potassium ion right here, and the silver ion and the nitrate ion right here. Everything is soluble, but when the silver ion comes into contact with the bromide ion, a precipitate starts to form, which is silver bromide, solid. And what's left behind? KNO3 is left behind, right? That's the idea. AgNO3, I take same AgNO3 and add it to, in this case, maybe like sodium iodide aqueous. What's going to happen? The source silver ion, the moment it comes into contact with the iodide ion, it forms AgI solid and NaNO3 aqueous. But I also know, this is the full equation, right? The full equation, including the spectator ion. But if I were to write, if this is equation C, and I were to write the equation C as the ionic equation, what would be the ionic equation? The ionic equation is simple. The change is the ionic equation. So sodium ion and nitrate ion are the same from left and right. No change. But I know that the silver ion and the iodide ion are precipitating to form AgI. So the silver ion reacts with the iodide ion to give you AgI. And this type of reaction is called a precipitation reaction. Now, why are we doing this reaction? We are doing it to identify whether you have the chloride ion, the bromide ion, or the iodide ion, right? And the way you do that is you add silver nitrate aqueous to the solution, and you end up with AgCl, AgBr, AgI. Now, how would this kind of tell me that, the chloride ion was present, the bromide ion was present, the iodide ion was present? Because of their colors. Because of their colors, I would know whether the chloride ion is present, the bromide ion was present, or the iodide ion was present. So what do you mean? So silver chloride is basically a what precipitate? It's a white precipitate. Silver chloride is a white precipitate. Done? Silver bromide is a cream precipitate, whereas silver iodide is a pale yellow precipitate. Pale yellow precipitate. And so if a white precipitate formed, that would mean that you had the chloride ion present inside this acid solution. If a cream precipitate was formed, that means that I had I had bromide ions in that solution. And if a pale yellow precipitate would form, I would have the iodide ion inside the solution. So this is how you guys can actually identify the silver ion. Yes, you could also use NABR, KBR, whatever you want to use right here, Mahanur, because realize that all group 1 halides are soluble. All group 1 halides are soluble. If you want, I'll also upload the solubility rules that'll help you in paper 3 as well, which I've taught in O-level and IGCSE. LMS Castro-Bar rules, right? So that's the idea. It all has to do with solubility. And this type of reaction is called the precipitation reaction. It's not a redox reaction. It's not redox. Even if you check out the oxidation numbers, they won't be changing anytime soon. So it's a precipitation reaction, not acid-base reaction, not neutralization reaction, no thermal decomposition, no redox. It's called precipitation reaction because a precipitate is forming, right? Now, the way you did it in O-level and IGCSE was that, and this is the correct way, that even before you added silver nitrate here, you used to, add dilute nitric acid. Remember that? Or you would say acidify it with nitric acid. Remember O-level and IGCSE? Question number 3, ATP. So we used to add dilute nitric acid and then we used to follow it by silver nitrate. And then we would get these 3 observations, either white PPT or cream PPT or pale yellow PPT. Yes? If it was PPT, you don't need to write PPT in the exam, you have to write completely precipitate. If it was AgCl, it would be white. If you had the bromide ion, therefore AgBr would form, it would be cream. And if it's yellow, that means you had the iodide ion, this is AgI, which is forming, right? And we used to acidify it with nitric acid, right? Acidify with dilute nitric acid. Nitric acid is HNO3 aqueous. HNO3 aqueous. And why would we do that? Your teachers never taught you this, but we used to do that to remove impurities. Sir, what sort of impurities? Your teachers would just tell you that you used to remove impurities with it, but it's now AS level. So I want to give you guys a little more detail for this. What sort of impurities do you actually remove? Basically, we try to remove the impurities which are the carbonate ions. Why, sir? Why do you want to remove the carbonate ions? Because the problem is that there's carbon dioxide in the air which can dissolve in a particular solution to give you carbonate ions. So this solution becomes contaminated, and if there's carbonate ions and you add silver ions, silver nitrate, the silver ions would come into contact with the carbonate ions, form Ag2CO3, which is also a white precipitate. So you would be confused. You would think, hey, is this because of the chloride ion or is this because of the carbonate ion. That is the reason why we used to first add it with an acid, because we know that all carbonates, they can react with acids. And what is that going to give you? For example, it was sodium carbonate inside the solution. So what would it give you? It would give you sodium nitrate, water, plus carbon dioxide. So this carbonates which would be present would evolve in the form of carbon dioxide. So why do we add dilute nitric acid? We add it to remove impurities. What sort of impurities? Well, normally the carbonate ions. Why? Because carbon dioxide is in the air, can dissolve in water somehow to give you carbonate ions. Silver ions could come into contact with it. That would also give you the white precipitate, and you'd be confused. Is the white precipitate because of silver carbonate, or is it because of silver chloride? So this is a precaution. Even when you are performing an experiment in paper 3, this is the precaution. If you are asked, why are you adding the acid? Or if you forget to add the acid and you end up with a white precipitate, what's the problem with that? Because now you can't be sure. You can't be sure whether it's because of the chloride ion or whether it's because of the carbonate ions. And that's the reason why you need such precision in such experiments to be dead sure that it's the white precipitate is because of the chloride ions. Now there's a problem with these precipitates. That's the new stuff. There's a problem with these precipitates. What's the problem with these precipitates? That's something new. What's the problem with these precipitates? In O levels, you're not taught the problem with these precipitate, but in AS level, you should know the problem with these precipitate. And the problem with these precipitate is this. That's the new stuff for AS level. This is the problem with the precipitates. Although this is like, a little over exaggerated in this picture, but this is the problem with these precipitates. Absolutely, Aisha. Aisha is right, sir. Practically, it's difficult to distinguish between them. It's hard to identify. Everybody's right. That's the problem. So if this is the problem, these colors are similar. This is the problem. So what do you need to do? This is something new for AS level. What we do is, it's pretty simple. We take them and we add dilute ammonia to it. In the first step, we add dilute ammonia and then we add concentrated ammonia. It's like a further test. Dilute ammonia and concentrated ammonia, right? Now what would happen is, if the chloride ion, if you talk about the chloride ion, aka the white precipitate, it's practically difficult to distinguish between them. So if it's AgCl, and you add dilute ammonia to it, do you know what's going to happen? The AgCl right here, this chloride ion is form of AgCl, right? What's going to happen? If you add aqueous ammonia to it, dilute aqueous ammonia, few drops, it would dissolve. And aka, I say it's soluble, or you could say it dissolves. The precipitate dissolves to give you a colorless solution. Literally, the precipitate dissolves. Right here, even with a few drops of aqueous ammonia. So what would happen in a lot of, in concentrated aqueous ammonia? What would happen in concentrated aqueous ammonia? Well, in concentrated aqueous ammonia, it's obviously soluble, right? So in both cases, soluble, right? Dilute ammonia or conc ammonia, in both cases, it's soluble, right? It dissolves. Silver chloride, which is a white precipitate, is going to dissolve. What if you have silver bromide? What if you have silver bromide, effectively the bromide ion? What's going to happen? If you add dilute ammonia to it, sir, it does not dissolve. Insoluble. It doesn't dissolve. But the moment you add conc ammonia to it, it's soluble. Done. The cream precipitate dissolves. So if I take these 3 test tubes, and in the first case, I add dilute, or I'm going to erase this. If I add dilute ammonia to it, and it dissolves immediately, what does that mean? It means that this was AgCl, and aka this was the chloride ion. In this solution, you had the chloride ion. But if I add conc ammonia, and it still dissolves, again, it's the same thing. If with dilute, it dissolves, and with conc, it also dissolves. What if I take dilute ammonia, and I add dilute ammonia to it, and it's insoluble? What does that indicate? That indicates that it's probably the bromide ion, probably silver bromide. But the beauty is that even with silver iodide, it's insoluble right here. So now you'll be confused. You'll be like, hey, if dilute ammonia ke saath, it's insoluble, it can be both. It can be silver bromide And it can also be silver iodide because both are insoluble. But remember, the moment I add conch ammonia, do you know what happens? The silver bromide, obviously, if it's silver bromide, it's going to dissolve, aka it's soluble. And if it's silver iodide, it's insoluble, which means it doesn't dissolve. So if the precipitate remains even after conch ammonia, that means you had silver iodide present. Do you know how I've remembered it throughout the years? I'll also teach you that. I remembered it like this. For chloride, it's soluble. For bromide, it's insoluble. For iodide, it's insoluble. See, first both sol, then insol, then inso. That's how I remembered it throughout the years. And why does this happen? Not a part of your course. Probably if I get to teach A2 chemistry, I'll tell you. It has to do with complex ions. The reason why it dissolves is because this silver chloride tends to become soluble because it forms complex ions with ammonia. What are complex ions? Story for another day. Complex ions. Similarly, silver bromide forms complex ions with concentrated ammonia. You just need to know complex ions. That's why it's soluble. Complex ions in this case are soluble. And this does not form complex ions. That's why not soluble. This forms complex ions in both cases. So that's how I've remembered it throughout the year. So it's practically a little difficult to distinguish between the two. That's why we use a further tactic called either adding dilute aqueous ammonia or conch ammonia solution. Simple, right? Simple as a pimple. If I ask you guys a question, I just need 15 to 20 more minutes and then we're done, inshallah. 15 to 20 more minutes, are you guys willing to give that to me? Because I want to just quickly get this over with, right? 15 minutes more, please. If I have, now please listen to this very carefully. An MCQ. I'm just testing your concepts. If I have dilute ammonia and I say the part A, solution is soluble. The solid dissolves. What does that mean? Part B doesn't dissolve, aka is insoluble. Part A का क्या मतलब है? Which ion would you have? And which compound? Well, the compound is silver chloride because if it's soluble with dilute ammonia, aka is silver chloride, and therefore you had the chloride ion, right? If it's insoluble, it can both be silver bromide or it can also be silver iodide. And so now I have to further get into another test, which is what? If it's insoluble, I add conch ammonia now. Now, if in conch ammonia, part A, if it's soluble, that means it's the bromide ion that was present. And part B, if it's still insoluble, the precipitate remains. Insoluble means it does not dissolve, the precipitate remains. That means you had the iodide ion. That's effectively how it can be tested in MCQs. Yeah. बस कुछ और बातें बतानी है and then we're done. That's the reaction of halide ions. So it's also called a reaction of halide ions with silver nitrates. And it's also known as the identification of the halide ions. So this is that. Easy, guys. Any questions up until now? So I call this D1 reactions. D1. D1, precipitation reaction of halides. D2 reaction. And this is by far the most important reaction of your entire inorganic chemistry. The most important reaction and 1000% tested in every single paper. 1000% tested, especially about 3 MCQs every single time. 3 MCQs and theory, a lot in theory. This is so important, and the conceptual understanding of all of this is very, very important. Which is that you take these halides, you can take these halides, and I'm just going to take it in the form of a salt. So I'm going to take sodium as my salt, right? So sodium chloride as my salt, sodium bromide as my salt, and sodium iodide as my salt. You could also take potassium bromide, iodide, chloride, same thing. So whatever reaction is true for sodium is also true for potassium, right? Same things. So in the exam, he can also give you sodium chloride, sodium bromide, sodium iodide, and he can also give you potassium chloride, bromide, iodide. So I can take these halides, these salts, I can take these halides and I react it with concentrated H2SO4. Right. Now, what's the purpose behind this reaction? Hanji, what's the purpose behind this reaction? Why does this reaction take place in the why does this reaction happen in the first place? I want to conceptually clarify everything for this reaction. No confusion whatsoever. Why does this reaction take place in the first place? Well, if I look at the halides, are halides reducing agents or oxidizing agents? Is chloride, bromide, iodide a reducing agent or an oxidizing agent? Shabash, please. I want a correct answer for this, please. Chloride, bromide, iodide, reducing, oxidizing, reducing agent, oxidizing, reducing agent, oxidizing, reducing agent. They have an extra electron. They want to give it to something else. So they are reducing agent. And the reducing power increases or decreases down the group. The chloride ions, the bromide ions, they're all reducing agents. Right? So aka sodium chloride, sodium bromide, sodium iodide, they're all reducing. Just like if I replace this with potassium, remember potassium iodide was one of the strongest reducing, one of the most popular reducing agent that you had studied in O-level and IGCSE. Because potassium iodide is the strongest reducing agent, right? It has the reducing power increases down the group, and you know why, right? So these are reducing agents, and down the group, the reducing power increases. True. So if you have a reducing agent, reducing agents would react with what? A reducing agent would obviously want to reduce something. And what would it want to reduce? It would want to reduce this fella right here, because conc H2SO4 is a pretty strong oxidizing agent. And see, that's the idea. That's the idea. Remember when I gave you guys the full picture of chlorine reacting with sodium bromide? Remember I told you the reason why this reaction takes place because one is an oxidizing agent and the other one is a reducing agent. That was the full idea. So oxidizing agents react with reducing agents, right? Please understand, is dilute sulfuric acid, this came in the MCQ one, so I just want to clarify this. Is dilute sulfuric acid an oxidizing agent? No. It's conc sulfuric acid which is actually the oxidizing agent, right? So maybe it depends on how, as in how strong of a reducing agent it is. Yes, Aisha. So we have these reducing agents, which is sodium chloride, bromide, iodide, right? And which of these is the strongest? It's sodium iodide, or you could even substitute it with potassium iodide. Remember that funny fella? Potassium iodide, the strongest reducing agent, because iodide ion has the highest reducing power compared to the bromide ion and the chloride ion, right? And so they would want to oxidize sulfuric acid. They would want, and out of these three, which one is the weakest reducing agent? Chloride, bromide, or iodide? Which of these is the weakest of the reduce? See, now I'm not writing sodium anymore. You know why. Why am I not writing the sodium ion anymore? Why am I not writing the sodium ion anymore? I couldn't care less. Couldn't care less. It's the what? It's the spectator ion. Couldn't care less. Khair. Now, between these three, which of these is the strongest reducing agent? Please identify that for me. Which of these is the strongest reducing agent? I'm repeating myself over and over again because it's very important to understand this reaction and not rote learn it. This is the strongest reducing agent, right? And conc sulfuric acid is the oxidizing. Please, dilute sulfuric acid is not an oxidizing agent. Conc sulfuric acid is the oxidizing agent. If I ask you a general question without having taught you anything, if I ask you a general question, this is the strongest reducing agent, right? And this is the weakest reducing agent. If I ask you a general question, which is the chloride ion, the bromide ion, or the iodide ion, which of these ions would oxidize sulfuric acid the most? Sorry, which of these ions would reduce sulfuric acid the most? Not oxidize, reduce sulfuric acid the most. They're all reducing agents, right? So they're going to reduce sulfuric acid. Which of these would reduce the sulfuric acid the most? Without having taught anything, you should know that. Which one is the strongest reducing agent? It's the iodide ion. So effectively, sodium iodide would be the one. Absolutely right, Ryan. Sodium iodide would be the one that would reduce sulfuric acid the most, which means it would mingle with the oxidation numbers of sulfur in sulfuric acid. And you know, these reactions are so funny. These reactions are so funny and so dangerous that every time you perform a reaction with conc sulfuric acid of these reducing agents, please understand that it produces one or more toxic gases. it produces one or more toxic gases. And that's why this reaction should be, performed in a fume cupboard. If this reaction is being performed in your classrooms, you are cooked. You should report to your teachers. This should be performed in a fume cupboard. I've not taught you the reaction. I'm just initially discussing things, but this should be performed in a fume cupboard. If you don't know what a fume cupboard is, search it out. Your teachers should have taught you that in O levels and IGCSE. In ATP, I've taught that. If you don't know, chalo, I'll show you the picture of a fume cupboard. That's how a fume cupboard looks like. This is the fume cupboard. So this is an inverted picture of the fume cupboard, but this is how it looks like. Probably your schools would not have this. Most of the schools wouldn't have this. If they do, then you are pretty rich. So this is a fume cupboard. You need to perform it here inside this fume cupboard to be protected from these toxic gases. So nonetheless, we figured out that chloride ions, bromide ions, and iodide ions, out of these, which would reduce sulfuric acid the most? This would reduce sulfuric acid the most, right? Sulfuric acid is the oxidizing agent. So this would reduce sulfuric acid the most. Right? That's the idea. And now I'm just going to go into the reaction. So let's talk about the chloride ion first. And obviously this would reduce it more than this, but less than this. Less than this and more than this. Right? We know that stuff. Because reducing power increases down the group. And this is so fun. Now you're going to enjoy it. Let's talk about the chloride ion and its reaction with sulfuric acid. I'm going to write sodium chloride. You could write the ionic equation. You could write the full equation. I'll write the full equation. You could write the ionic equation later on. Now I'm going to take conc sulfuric acid, H2SO4, conc, concentrated sulfuric acid, conc sulfuric acid, right? And so if I took H2SO4 conc, what is going to happen? Sodium chloride is going to react with sulfuric acid. And can you guys tell me the oxidation number here? It's +1. This is -1. Can you guys tell me the oxidation number of sulfur? I'm not even concerned about this oxidation number. Can you guys tell me the oxidation number of sulfur? Hanji, what is the oxidation number of sulfur? It's +6. You should know this by now. We've done so much practice, basically sulfate ion. You could calculate it, This is X, this is -2, -2 times 4. Add them together. This is -2, X equals +6. Hope you all remember this stuff, right? So sulfur has an oxidation number of +6. Now you have a chloride ion here eyeing down this conc sulfuric acid. It's eyeing down this. Now my question to you guys is, what's the reducing power? What's the reducing power? Yes. How much reducing power does the chloride ion have? Is it the strongest reducing agent or is it the weakest reducing agent? The chloride ion, not talking about chlorine, chloride ion. It's the weakest reducing agent. Weakest. Right? And what we do is, practically speaking, we drop H2SO4 on top of this sodium chloride crystal. Slowly, we drop them slowly onto NaCl. This is how we perform it practically. If you want me to show you the practical experiment for it, even it's this right here. This is how practically it's performed, right? So this is sulfuric acid, conc sulfuric acid, and these were crystals of sodium chloride, and you slowly used this funnel to, to drop by drop add conc sulfuric acid here, and see what's being formed. Sir, hydrogen chloride is formed. A gas called HCl is formed. Why does HCl form? See, the hydrogen in the acid and the Cl would form HCl. That's why I told you that you need to perform this in a fume cupboard, because these white HCl has a white steamy fumes, cloudy fumes, white steamy fumes, white steamy fumes, white cloudy fumes. We've also covered HCl in the prior chapter when we were studying group 2, white steamy fumes, or periodicity, period 3, in which we used to take what did we used to do? We used to take PCl5 and add it to water. Remember? What would happen? You would get H3PO4 and you would get HCl, these steamy fumes right here. Similarly, all the others, when added to water, we would get, like for example, SiCl4 plus H2O. What would you get? You would get, get SiO2 plus HCl, right? Why SiO2? Si and O, and then H and Cl, right? So this is how we studied that these white steamy fumes form. So whenever HCl gas is forming, it's white steamy. Even HBr, even HI, they are white steamy fumes. अच्छा हम कहीं और चले जा रहे हैं. Let's come back to the topic. Now this is the weakest reducing agent. HCl forms. What else would form? You know what happens? One of the H and one of the Cl, when they go together, they form HCl, right? What is left behind? My question to you guys is, what is left behind? Can I say that if one of the H's and one of the Cl go together to give you HCl, what is left behind? You're left with H, one H goes, so you're just left with HSO4. You're just left with HSO4 negative ion. This is the negative ion which forms, you know. SO4 2 minus is the sulfate 2 minus ion, right? And if one of the hydrogen goes and forms H and reacts with the Cl, forms HCl, it is HSO4 minus which is left behind. And on this side, you have the sodium ion which is left behind. And how do you write the formula? You write the formula like this: sodium HSO4. This is what is left behind, right? Now, why was I telling you that Cl is the weakest reducing agent? What was the idea behind it? Can you tell me the oxidation number of sulfur right here? Can you guys tell me the oxidation number of sulfur right here in the HSO4 negative ion? Can you guys tell me the oxidation number of sulfur? And obviously, yeah, shabash. Jaldi bataएं. And obviously, it's what? It's plus 6. HSO4 minus, this is plus 1. Sulfur, I don't know. Oxygen is minus 2. Minus 2 times 4. Add them together. Gives me what? Minus 1. What does that give me? X minus 8 plus 1 equals minus 1. X minus 7 equals minus 1. Udhar gaya. X equals plus 7 minus 1 equals plus 6. What does that tell you? What has the chloride ion done? What has the chloride ion done? It has done what? It has done this. That's the beauty. That's why you needed to know this stuff. The chloride ion does not reduce conc sulfuric acid. How did I know? Plus 6 plus 6. Nothing happened. It's just HCl being formed and a solid sodium hydrogen sulfate, NaHSO4 solid forming. That's it. That's it. Nothing else. Acha, why is this downward? Why is this downward delivery? Because HCl is denser. As all of this should be known to you guys in O levels and IGCSE. HCl is denser than air. That's why when HCl is collected through the downward delivery, the air is displaced upwards. Will this be tested? No. I'm just teaching you practically. This is the experiment. Yes. So H2SO4 is a strong oxidizing agent. It's a strong... Now, there are two ways to imagine this. You could say that the chloride ion is the weakest reducing agent, and therefore it does not have that much reducing power to oxidize H2SO4. You know, you could also say this in the MCQs. These are all MCQ perspectives. You could also say that H2SO4, conc H2SO4, is not a strong enough oxidizing agent to oxidize chloride ions. That's also one way of framing it. So you could either frame it from the perspective of the chloride ion, which is the correct perspective. I like this better. It makes much more sense to me than this perspective. But you just flip this up. You say chloride ion does not reduce H2SO4, conc H2SO4, because it's the weakest reducing agent. Or you could say conc H2SO4 is not that strong to oxidize chloride ion. How do I know? So this is Cl is minus 1 here, and it's still minus 1 here. So these are the two things I'd eye down. The sodium ion, the hydrogen ion, they are all spectator ions. Nobody cares. So these are the two things that I eye down. The minus, the plus. Nothing happened. Nothing. So conc H2SO4 did not oxidize chloride ions. did not oxidize NaCl effectively. And your chloride ions or NaCl did not reduce conc sulfuric acid. Done. This is reaction number A. And that's it. It finishes. Nothing else. Nothing else. Now, and why does this happen? Why does this happen? Why does this happen? Again, because of reducing power and oxidizing power. We all know that. Yes. Next, part B. Part B. अच्छा, part B की बात कर लेते हैं. Bromide ion. The first bit is the same. So let's suppose I took potassium bromide or sodium bromide, reacted it with sulfuric acid, conc sulfuric acid. The first bit is the same. Hydrogen and Br, white steamy fumes of HBr will be observed. White steamy fumes of HBr will be observed. What is left? What is left behind? You have the sodium ion which is left behind. And here one hydrogen is left. So you just have HSO4 minus, because hydrogen is positive. If a positive leaves, it becomes minus, right? So sodium ion, HSO4 minus ion, right? So what do you get? NaHSO4, right? So the first reaction, this is how step by step it happens. The first bit is the same. Just like it happened with the chloride ion, it's the same for the bromide ion. See, I'll even prove it to you. This is -1, this is +6, this is +6, and this is -1. Everybody agrees with me. The initial reaction is the same. And what is the observation? The observation is steamy fumes, white fumes, steamy fumes, white fumes of HBr. Don't need to write HBr, but I'm just saying it's HBr's white fumes. That's the observation for A. That's the observation. Please, at every step, you need to know observations. B. Now what's going to happen? There's also something else. A part 2, effectively. A part 2. And it's pretty fun. The fun bit is that the Br minus ion, is it a stronger reducing agent compared to the chloride ion or a weaker reducing agent compared to the chloride ion? Stronger reducing agent or weaker reducing agent? Stronger reducing agent, weaker reducing agent. Yeah? Stronger, weaker. It's stronger reducing agent compared to the chloride ion. Everybody agrees with me. It's stronger reducing agent. Huh? Sir, if it's stronger reducing agent, it has not done anything to sulfuric acid. Well, it does. Hold up a moment. It does. This is +6, +6. Initially, it doesn't do anything. But this HBr, this HBr, the HBr that has formed, this will further react with sulfuric acid. And what is it gonna do? When this HBr reacts with sulfuric acid, you know what it does? It makes sure that sulfuric acid goes from +6. The sulfur in sulfuric acid goes from +6. It wants to reduce it, and it can reduce it because it has the strongest oxidizing. It has stronger reducing power compared to chloride ions, right? So the bromide ion has a stronger reducing power compared to the chloride ions, and therefore it will make sure to go make this sulfuric acid reduced. And how do we know it's reduced? The oxidation number would change. It would change from +6 to +4. And how does it change from +6 to +4? Well, it forms SO2. What is SO2? Sulfur dioxide, right here. And sulfur dioxide is a reddish brown gas. No, sulfur dioxide is not a reddish brown gas, sir. Sulfur dioxide is a colorless gas. Sir, then why have you written a reddish brown gas? That's SO2, right? Why have you written a reddish brown gas? What is a reddish brown gas? Red brown, red brown, red brown, red brown, red brown. Yes, 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 yes. Red brown is bromine. So Br2 gas also formed. And so you know something funny? You know something funny? That this Br concentrated sulfuric acid, this Br had the power of reducing concentrated sulfuric acid. And how did you see it? It went from +6 to +4 right here. And this Br right here, this was -1 oxidation number. It went from -1 to 0. So Kong's sulfuric acid was strong enough to oxidize the Br. It was strong enough to oxidize the Br in HBr, obviously. It was strong enough to oxidize HBr effectively, but it was strong enough to do that. And from the other perspective, you could say the Br was strong enough reducing agent to reduce sulfuric acid, and it made it go from +6 to +4. What else would form? It's basically H2O would form. So it's SO2, Br2, and H2O. How do you balance it? Pretty simple. So there are 2 Brs on the right. I'll add a 2 here. And there are 4 hydrogens on the right. 2 and 2. 4 hydrogens on the right, only 2 here. So I'll add a 2 here. Oxygens are automatically balanced. So this is the observation. Reddish brown gas. If a reddish brown gas follows, that means the HBr has done its thing. Yeah, makes sense? Now the last one. See, isme khudai kasam, I have never learned these equations, and you'll see in your classes. You'll see destruction in your classes. That's why I taught redox first. So the pattern of my syllabus is in such a way that it's very coherent. I know which chapter is used in which chapter. The last one, the iodine. Now you guys tell me. The first two would be the same. Can you guys write the first 2 bits? A1 and A2 for me. So let's use sodium iodide. You could do even the ones that are true for sodium iodide, it's also true from potassium iodide. Kong's sulfuric acid gives me what? Acha, NaHSO4 is a solid. So you won't see a solid disappearing anytime soon. Acha, what's going to happen? Again, the first step the same. Sodium ion, and so H and I will form Hi. Definitely Hi is going to form, and obviously Hi is white steamy fumes. Done. White cloudy fumes, white steamy fumes. What is left behind? HSO4 minus, and so what forms? NaHSO4. Done. Initially same, +6 -1 -1, nothing changed. But then you know that this H I will be like, hey, mamacita. It will react with Kong's sulfuric acid and say, hey, I'm gonna make you go from +6 to +4, SO2. Be ready. And then I myself, I'm gonna go from -1 to 0. How do I go from -1 to 0? I2. Right? And what else is formed? H2O. Pretty simple. Pretty simple. So initially you see white fumes of Hi in this case, and here what do you see? I2 is a purple vapor. I2 gas forms, right? So it's a purple vapor, and you see a colorless gas. Purple vapor is for the I2, and colorless gas is for SO2, and this is I2. Done. So these are the 2 observations. Done. But now my question to you guys is something different. My question to you guys is that iodine, this I minus right here, this I minus right here, is it the strongest reducing agent or the weakest reducing agent? Strongest or weakest? Strongest or weakest? And you can even balance this. Put a 2 here and put a 2 here. I think it's balanced. Yeah, it's the strongest reducing agent. So it doesn't just take this +6 to +4. It also says, hey, I'm not going to just take you from +6 to +4. I'm going to take you from +6 to +4, and then I will also take you from +6 to, I can also take you from +6 to 0. I can also do that with you. I can reduce sulfuric acid so much that I can even take it to 0. And how would it do that? Again, the A part 3. Hi says, hey, hold up, I'm gonna wanna shana mana take you from +6 to 0. How does sulfur attain the oxidation number of 0? You tell me how it does that. You tell me how it does that. Come on, you tell me how it does that. When would sulfur have an oxidation number of 0? S. Sulfur, pure elemental state, oxidation number of 0. You know, oxidation number of 0. And again forms I2 plus H2O. Done. I2C -1 से गया 0 पे खुद it is oxidized and reduced sulfur. It made sulfur go from +6 to 0 right here. And it says not even that. I will make you go into negative sulfur. I will make you go into negative sulfur. Sir, what? How can you make me go into negative? Sulfuric acid, I can reduce you so much that I will make this sulfur in sulfuric acid go from +6 to -2. How do you go from +6 to -2? H2S. That's -2. Because you've calculated the oxidation number of sulfur right here. This is +2. Or hydrogen is +1, but you have 2 hydrogens, so +1 times 2 plus x equals 0, x equals -2. I will take you to -2, and again I2 forms and H2O forms. That's it. That's the idea. That's the idea. And so these are my beautiful reactions. If I were to balance them, please listen for the balancing. Balancing sometimes becomes a little difficult. So in A2, what has happened is it took it to +4. Then in A3, it can also go from +6 to 0. And so what's the observation here? Sulfur is a yellow solid, a brittle yellow solid. So here you see a yellow solid. If you see a yellow solid, know that Hi has taken sulfuric acid to 0. The oxidation number from +6 to 0. A yellow solid forms, and because you have I2, you also see purple vapors forming. So purple vapors and yellow solid. Similarly here, hydrogen sulfide, so purple vapors form. And hydrogen sulfide right here. Hydrogen sulfide has a very strong smell like bad eggs. The way rotten eggs smell. So it has a strong bad egg smelling stuff. Sir, how do you know that? How would you know how much it reduces it? Rayan, sulfur can have oxidation state of +6, +4, +6, +4, 0, -2. So chlorine doesn't do anything, remains here. Bromine does this and this. And iodine, why am I saying chlorine, bromine, iodine? Sorry, chloride doesn't do anything. Bromide does this and this, right? And iodide does this, and this. That's how you remember it. So let's balance it first, and then I'll give you a quick summary. So what we do is we balance out the oxygens first. You have 4 O's on the left, and you have 1 O on the right, so I'm going to add a 4 here. Then you balance out the hydrogens. You have 4 times 2, 8 hydrogens on the left, and you already have 2 hydrogens on the right. You have 8 hydrogens on the right, and you already have 2 hydrogens on the left. I don't want to mess with these because then I'll have to mess with the O's again, so that'll be a problem for me, right? So I first balance out the O's. You have 4 O's. 8 H's on the right, you already have 2 here. How many more H's do I need? 6 more. So what should I multiply 1 with to get 6 more? X is equal to 6. I get 6 H's here, and in the end I just balance the I's. S is already balanced, so I's, you have 6 I's here. I'm gonna put a beautiful 3 right here, and that's the balanced equation right here. Next, if I look at this fella right here, it's basically 2 hydrogens here and 2 hydrogens here. But I first of all have to look at the O's. Always look at the O's first. So 4 O's on the left, and how many O's do you have on the right? Only 1. So what should I multiply 1 with to get 4? Obviously my beautiful number 4. Then I have how many hydrogens on the left? 2 plus 4 times 2, 8, 10. 10 hydrogens on the left, and you already have 2 here. So I need 8 more. What should I multiply hydrogen with to get 8 more? X is equal to 8. I'm going to add an 8 here. And then you just balance out the I's. You have 8 I's on the left, and how many I's do you need on the right? You need 8, right? So what should I multiply 2 with to get 8? X is equal to 8 over 2, that's 4. And that's how you beautifully balance this stuff out. Summary suniega. The summary is, if you have the chloride ion, it does not, what are the products with the chloride ion? The products with the chloride ion are HCl. Obviously NaHSO4 forms, but that's the oxidation state. That's also a product. So HCl and NaHSO4, right? Then with the bromide ions, you have what? What do you have with the bromide ions? Well, with the bromide ions, you have HBr, and you also have Br2. Done? That forms. And for sulfur's oxidation state, it gives you +6, and it also gives you +4. Done? Then with iodide ions, you get HBr, you get HI, and you get like I2. What about the other products? For sulfur's sake, you get NaHSO4, which is plus 6. You get SO2, which is plus 4. You get H2S, which is what? H2S before H2S, you get sulfur 0. You get H2S, which is negative 2. So that's the idea. That's the idea. And the conclusion is it is easier to oxidize the hydrogen halides down the group. It is easier for sulfuric acid to oxidize the hydrogen halides down the group. And it's also easier for the hydrogen halides to reduce concentrated sulfuric acid down the group. Yes. So these reactions were very crucial. And one last thing, एक आखिरी चीज. Just give me a moment and मैं एक आखिरी चीज पढ़ाना चाहता हूँ and then we're done. So the last couple of things that I want to teach you guys, और बस फिर we're done, is that, and this will help you in organic chemistry. So I will come back to this in organic chemistry, remember, and it is connected with organic chemistry, which is that why is it not a good way to prepare HBr or HI by reacting, and this has never been tested, but why is it not a good way to prepare HBr or HI by reacting NABr or NaI with conc sulfuric acid? Why? Shabash. Who is gonna answer this? Why is it not a good way to prepare HBr or HCl? You can prepare HCl by taking NaCl and reacting it with conc sulfuric acid, but we don't do this. And you will come across this in organic chemistry. Remember, I'll ask you this in organic chemistry. So why is it not a good way? Why do you think? Suggest why it's not a good way to prepare HBr or HI by reacting NABr with NaI. See, you can react NABr with NaI, and either or would happen. This can happen, but I taught you guys all the possibilities, right? This can happen. Now, why is it not a good way? Because the moment you take NaI and react it with sulfuric acid, forms HI. The HI can further react and form I2. This will further react, form I2. The HI can further, the HBr and HI can further oxidize the sulfuric acid, right? They further reduce sulfuric acid and themselves get oxidized. So HBr, HI can form, but they're going to further oxidize themselves by reducing sulfuric acid. So it's not a good way to prepare it, and Rayan is right. It can go up to S, it can go up to SO2, H2S. So the HBr or HI that forms, further oxidizes. So you never really get them. It further oxidizes. This with NABr and NaI, you get a mixture of gases. Because you can get SO2, you can get H2S, you can get, you could get Br2, you could get all of these mixtures. So you get, these are the 2 points. This I've taken from one of the books. That's why I was searching it. What was that question that I thought that I would teach you when I read that book? So I was searching this question in the book. So this has never been tested, can be tested, and I will prove it in organic chemistry. I will use this idea in organic chemistry. So always remember it. One last thing to further consolidate everything. Is you might be noticing something, which is the first reaction is the same. The moment HI forms, HI can reduce this HI can reduce this to SO2, HI can reduce this to S, HI can reduce this to H2S, right? HI can reduce this to SO2, S or H2S. Similarly, HBr can reduce this to SO2 as well, right? But HCl which forms, the HCl that is forming, where is it? The HCl that is forming is not further reducing sulfuric acid. Why? The last idea, which is, see, again, HCl, HBr, HI. Which of these have the weakest bond energy. Weakest. And because it's the weakest, it is most reactive. So you could have also thought from this perspective. So there are 3-4 different perspectives you can think about when you write these equations. Yes, these are also products. Please understand, these are also products, but they are related to sulfur's oxidation numbers. See? These are I've segregated them between two products. This forms, these two forms, and these two form, and this, right? That's the idea. Any questions, guys? Any questions whatsoever? कोई सवाल शक शुबा पूछिएगा.